All right, here's another application of dot products and a few other things put all together. This topic is going to be called projections. And projections between two vectors is not a hard topic, it's just a lot of symbolism. So the first thing you have to imagine is someplace up here is the sun. You draw him in, a little diagram of the sun. And the sun's rays are coming down perpendicular to V. So when they're coming down, they're going to come down perpendicular to V. And in that way, if you think of U as like a tree or a solid object, the sun rays are going to get cut off here, and they'll never make it to V, and you'll get a shadow that is formed here at the very end of vector U all the way down to vector V. So this side of this triangle, from here to the origin, we're going to consider this our projection. So let me go through all the little pieces that make up a projection. Number one, we have the drop line. So you're going to the end of U and you're dropping it onto V. So this is going to be a projection of U onto V. And the way we're going to denote that, and I'll write it down several times, the projection of U onto vector V. It would look something like that. Alright, so step number one, we're going to drop this down. It's going to create this point on vector V. There's two pieces that we need to create any vector. If we know their magnitude and the direction they're going in, then we can create any vector going. So that's the goal here. We're looking for the magnitude of this vector that goes along here. I'll draw it in, all the way to this point I just created. If I can find the magnitude of that and the direction, then I'll know what the equation or the vector will be equal to. Alright, so here we're going to create something that'll help us out. Number one, if we use this angle, that'll give me some kind of idea of direction. And also this unit vector. Now remember, with little hats on top, that means unit vector. So we're going to take vector V, which could be any length whatsoever, and we're going to make it a unit vector because they're easier to scale to be bigger or smaller. So this will give us our direction. So this is direction. The theta will come in handy a little bit later. Alright, so the next thing I need to know is the magnitude. So I need to find the length of this side here, all the way down. So if we go back to like polar coordinates, I know the length of I know the length of the side according to the magnitude of the vector up here and the angle of separation between the vectors. The length of the side is going to be the magnitude of U cosine of theta. Cosine of theta. And we could have set up a right triangle trigonometry. The cosine of this angle is equal to the unknown over the magnitude of U. When we solve for the unknown, the magnitude of U moves over next to the cosine of theta. Alright, so here I have magnitude of cosine of theta, and here I have the direction, this unit vector of V. Okay, so let me switch pages. Here's my main picture. So here's my projection that I'm looking for. So this projection, let me shrink this thing down. It's kind of in the way. This projection is going to be the projection of U, vector U, onto vector V is going to equal the magnitude, which we found out to be the magnitude of U cosine of theta, times the direction, which is the unit vector V. Alright, so now we can use some other formulas to make this look a little bit nicer. Formula number one. Cosine of theta has its own little setup in relationship to U and V. It is equal to the dot product between the two vectors divided by the magnitudes of those two vectors. So we have that. We also can do the substitution of v hat here. V hat's formula is the vector, that's a u, vector v divided by its own magnitude. That'll shrink it down to, or grow it out to, a length of 1. Alright, so doing these little substitutions, we get that the projection of u onto v is equal to the magnitude of u. I'll leave him alone. The cosine of theta is now going to become u dot v over the magnitude of u, the magnitude of v. So we're just doing a direct substitution of what cosine of theta is equal to. And then we have this v hat here, so we'll multiply by the vector v divided by its magnitude. Now that's a lot of symbols, but we can break it down into scalar and vector. So let's break it down into scalar and vector. Magnitude of u, that's a scalar. U dot v, that's definitely a scalar. Magnitude of u, magnitude of v, that's a scalar. Magnitude of v over here is a scalar. So everything here is a scalar except for this one thing. This is the only vector out of this whole mess. So all these green circle things are just regular old numbers, and then it's going to be this huge scalar, or whatever the heck this is going to be, times vector v, and what that'll give me is this vector right here. We're multiplying vector v by some scalar to, in this case, shrink it down a little bit. If vector v was a little smaller, this calculation would make it a little bit longer up until this point. Alright, so let's simplify this mess. Move this up, need red. Let's kill a few things. Well, here the magnitude of u will cancel with this magnitude of u. I think that's the only thing that dies. So what's left is magnitude of v times magnitude of v, which is just, itself squared. So we get this nice little formula. The projection onto v of u is another way of reading that, is equal to u dot v over the magnitude of v squared, also known as v dot v, if you want to get fancy, times, and this is not a dot product because all of this is a scalar, the vector v. So again, scalar, and over here, vector. To keep things kind of straight, what's going on. So that is involved in the formula creation of the projection of one vector onto another. Alright, so let's use it a little bit. Let's say I have a vector u. It's -2, 5. Let's say I have a vector v that is, let's see, -2, 5. Let's put v someplace over here. Let's make it 2, 5. Alright, now it really does depend which one is going on top of which one. So I usually draw a picture just to make sure I'm doing it the right way. So vector u is pointing someplace over here. So here's u. Vector v being 2, 5 is pointing someplace, let's use a different color, orange, is pointing 2, 5 someplace over here. So if I do vector u onto v, you've got to kind of get an idea of where the perpendicular will happen. You get something that looks like this. And vector of u onto v would look like this short little vector here. So let's find that one. So we're looking for the projection of u onto v, just like up above. So I can follow the formula exactly. If the letters switch, the only thing you have to be careful about are these two letters. The small letter will always be the denominator and the vector you're going in. So if you switch it, this would become magnitude of u squared times the vector u. The dot product, it doesn't matter what order you do those in since it's commutative. Alright, so the projection of u onto v. So we're going to need two parts, u dot v, which is going to equal those two multiplied together, so -4. Those two multiplied together, 25, and add your answers. So this will become 21. And then we're going to need the magnitude of v squared. Now, you could do that v dot v, or you can just square these and leave the square root off. So you're going to get magnitude of v squared is going to equal 2 squared plus 5 squared. Now, if that square was missing, then it would be the square root of 2 squared plus 5 squared. But because it's squared, we can drop the square root. So that's 4 plus 25, which is 29. So this becomes 21 over 29 times the vector v, which is 2, 5. Now, if you want, you can distribute through and come up with just the two components, but this is a perfectly fine form also. Now, one thing that is a little strange, let me draw some lines in here. Let's say I have a vector pointing in this direction, and let's say I have another vector pointing in this direction. Oops, come on, there we go. Then when I try to do the green vector projected on top of the blue vector, I'm going to have to do a little adding in, because you can't draw a perpendicular back to this blue line. So you have to do a negative extension of the vector, and this projection would actually come down facing the opposite direction of the blue vector. So you'd get a scalar that actually is negative times the blue vector. And that's all there is to a projection.